In this video, we'll be covering section 8.1, Basic Differential Equations. We have 4 objectives. The first one is we will verify that a given function is a solution or is not a solution to a given differential equation. We will find general solutions to basic differential equations, very simple ones in this section. And then we will also solve initial value problems. And then we'll finish with looking at some applications of differential equations. For the most part, this section actually is not new. We have seen examples of differential equations before, so there might be some new terms, there'd be some applications maybe that we hadn't seen before, but for the most part, this really is not new. So if you want to try the assignment, I think it would be safe to maybe just go ahead and jump in and see how it goes, and if you're struggling, you could come back to the video and see if it helps. Okay, we're going to start off with just some basic ideas. So, differential equation. A differential equation is simply any equation that contains an unknown function and one or more of its derivatives. So these are 3 different examples of differential equations. In the first one, we can see there's a derivative of y here, and the function y is also in that equation. And then you have some other function, cosine of x here, but that's fine. In the second one, you have a second derivative of a function with the function itself. And then in this one, we have the first derivative of a function, and it's equal to this product involving the function itself. The big difference with differential equations and normal equations that we're used to is when we solve them, we're not solving for a numerical quantity. We're solving for a function. Our solution will be some function f of x. And we're saying that function has to satisfy the equation. Differential equations have what's called an order. And the order is simply whatever the highest derivative that occurs in the given equation. So if we look at the example from C here, this was a first order differential equation because the highest derivative is a first derivative. Where this one here is a second order differential equation because it has a second derivative. Now, differential equations can also be considered linear, and this is a little bit more complicated. It's not quite as simple as it is with just normal linear equations, even though there is a relationship. So both of these 2 differential equations are very complicated looking, but these are both linear differential equations. This is a first order linear differential equation. It's first order because the highest power, or highest derivative I should say, is first derivative. This one is also a linear differential equation, but it is a second order differential equation because the highest derivative is the second derivative. Now, what does it mean for it not to be linear? Well, linear differential equations cannot have powers of the function higher than 1. You can't have the function itself multiplied by any of its derivatives, or you can't have the function composed inside of another function. These would disqualify it from being a linear differential equation. So if we look at this first one here, this one is not a linear differential equation because when you distribute this through, you would have a higher power of the function itself. You'd have a y squared, and we're not allowed to have that. This one is not a linear differential equation because you have the function multiplied by one of its derivatives, so not linear. And then this one is not linear for a couple reasons. First is you have a power on the second derivative. We can't have any powers higher than 1 on either the derivatives of the function or on the function itself. So this would disqualify it, but so does this too. Here we have a square root, which would be a power of 1/2. So we don't want fractional powers on the variable itself, or on the function itself, I should say. Now, if you had the square root over here, that's not a problem. It is just you can't have the square root on the unknown. The unknown in this case is not x, it is the function itself. So another way to think of why this is a problem is I said you can't have the function itself composed inside of another function. So this is y sitting inside of a square root function, and that's not allowed. Okay, so let's talk about solutions. So as I mentioned, solutions to differential equations are functions. They're not just simple numbers unless the solution was a constant function. So let's say we look at this second order linear differential equation, and we want to verify that this function is actually a solution. So to verify that, we would just need to plug it and its derivatives back into this to see that it actually works. So let's start by finding the second derivative. So we need the second derivative in order to be able to plug that in. So we do the first derivative. The derivative of this is going to be negative 4 sine of 4x using chain rule. So then the second derivative would be negative 16 cosine of 4x. And then we already have y itself. So to test it, we're just plugging everything in to this and checking to see, do we actually get the same thing above. So let's plug everything into this. Y double prime is this, so that's negative 16 cosine of 4x. And then 16 plus 16 of y, this was y. All right, now if you simplify this, obviously these two things wipe each other out. So we can see clearly that this is going to come out to 0. So this proves, this verifies that yes, therefore y equal cosine of 4x is a solution to the differential equation y double prime plus 16y equals 0. Okay, let's look at another example. So still verifying solutions, and we're looking at exponential functions in this case. We will see that the more we do with differential equations, exponential functions play a very big role in differential equations. So you're going to see a lot of these. Okay, so this again says show by substitution that this function is a solution to this differential equation. So just as before, we can start off by finding the derivative. So differentiating this again using chain rule is going to give you 25e to the 2.5t. Remember, the derivative of an exponential is itself, but in this case we have to apply chain rule, so we multiply by the derivative of that exponent, which would just be 2.5, and I can go ahead and multiply it by the 10, which is where we're getting that. Okay, so now we have everything we need in order to plug into this. So this one's a little bit harder to actually kind of show the way we're plugging in, because it just looks like we're not doing anything. So I can put this right here, so 25e to the 2.5, and then I'm testing, does that equal this? Well, let's put it in. We got 2.5, and then I need to put y here. Y was this, so 10e to the 2.5t. So is that a true statement? Well, obviously you can multiply these together, and you do get a true statement. The left-hand side is equal to the right-hand side. So therefore, indeed, y equal 10e to the 2.5t is a solution to the differential equation y prime equals 2.5y. You'll notice I'm suppressing the t. That is very common. Typically, we will stop writing the independent variable there. We could put it on both of them though if we wanted. It doesn't just have to be on the derivative. This is saying the same thing as this. And there's no special reason for using t. For some reason, our book shifts over and uses t almost exclusively, but this could be x here. The independent variable is free to be anything. Okay, so that, okay, we do have a part B to this. So part B says, well, okay, that previous solution worked, but we're going to show that there's more than one solution, that in fact this is a solution to the differential equation always, no matter what C is. So I should have kept that differential equation up here. Okay, so we're just going to do the exact same process that we did before. So we need to do the derivative of this. It's going to work the same way again. So the derivative of this is itself, but we have to multiply, using chain rule, by the derivative of the exponent, which would just be 2.5. So we have 2.5c e to the 2.5t. That is the derivative of this function. Now we just plug it all in to this and see if we get the left-hand side being equal to the right-hand side. So this would be placed here, 2.5c e to the 2.5t. And then the question is, will that equal the right-hand side? If I take 2.5 and I multiply it by our, this one here, which is c e to the 2.5t. Is it the same on the left and the right? Obviously, yes it is. So therefore, y equals c e to the 2.5t is a solution to the differential equation y prime equals 2.5y. So what this illustrates is that a given differential equation could have infinitely many solutions. So every solution, we can put any constant we want in for c, and that is a solution to this differential equation. So the term for that is, this is what we will call a general solution. Whereas in the previous one, this was a particular solution. So we'll see more of that as we do some of the other examples. Okay, so some of the times you're going to be given what's called an initial value problem, or sometimes they're called boundary value problem. And that is where you'll be given a differential equation, like what we've been doing, but you'll also be given an initial condition on the function itself. Typically it's with the input of 0, but technically it could be any input. It wouldn't have to just be 0. So if we look at the same differential equation that we had in the previous example, this is the exact same one, but we've been given an initial condition. So we already know that the solutions to this are y equals c e to the 2.5t. Right? We just verified a second ago that this is what the solutions to this differential equation look like. So now we want to be able to find the exact value of c that satisfies this initial condition. So we know y of 0, if we plugged 0 into this, would be c e to the 2.5 times 0, but that would give us an exponent of 0. E to the 0 is just 1, so that would be all equal to c. Y of 0 is c, but they said that this is 3.2. So that means 3.2 is our c value. So the particular solution that we get is 3.2 e to the 2.5t. So this is the solution that satisfies the differential equation, but it also satisfies the initial condition. You can actually see what's going on in the image over here on the right. So all of these black curves, they represent the different forms for this. Right? There's technically infinitely many. I've only plugged in a few values for c's, but every single one of these looks like this. Right? And you'd even get more coming up here. So the idea is, though, we want the solution that passes through one particular point. That point being when you plug in 0, let's actually change the color of that. When you plug in 0 here, we want the y value to be 3.2. And there is only one of those curves that has that property, this particular one. That's our particular solution that passes through that point. So that's what we mean by an initial value problem. You find the general solution, and then you use the initial condition to get the particular solution. Okay, so we already kind of mentioned what the general solutions were. As I said, this was the general solution. It represents all of these, a family of curves. So let's try a few examples where we're doing general solutions. Okay, so on this one we have a differential equation, and this is what we would consider to be the nicest type of differential equation, because there is no function on, like the y is not on the right side here. All we have is a derivative, and we have the independent variables over here. So we don't need any fancy tricks for these. This is just a real easy one. The idea is you can just take the antiderivative. Oh, let's get back to blue. Take the antiderivative on both sides. All right, whatever I apply to the left-hand side, I should also do to the right-hand side. So right here, fundamental theorem of calculus tells us that these are going to cancel. They just wipe each other out. Now, technically, we would get y of t plus some constant. But you'll see in a second why this step is not really necessary. You don't really have to put the plus c here. All right, let's also do the antiderivatives of this. So what you're going to get for this one is a 5 sine of t, and then you're going to get minus 2 cosine of 3t. Technically, we would do a substitution on this, but you should just kind of be able to look at it here. The derivative of cosine is negative sign, so that will cancel this negative. And then chain rule says we will have to multiply the 3 on the outside, which is where the 6 comes from. All right, this one would also have a constant, potentially a different constant. So then we wanted y of t. So to get y of t, we would just subtract this constant over. These two constants could be combined, but it just generates a new constant. So we don't typically write them out as separate. We'll just put a single constant at the end of this. So 5 sine of t minus 2 cosine of 3t plus just a general constant c, because these two combine to give you a constant anyway. So that is our general solution. If you needed a particular solution, they would have to give you some kind of an initial condition, like y0 equals 8 or something like that, and then you could come back and solve for the appropriate c. But this one did not give us that, so we don't need to do it. Let's try another one of these. So this one, they gave us the second derivative, so we'll need to do the same process twice. So we'll first take the antiderivative on both sides. So over here, when we take the antiderivative, we will just get the first derivative. And again, I'm not going to put the c, we'll just put the c at the end over here. Okay, so antiderivative for this is going to be 10t to the 4th over 4 minus 144 t to the 8 over 8 plus 12t squared over 2. And then we're going to add a c here, but I am going to put a subscript on it. And the reason is we have to do this process again, which will actually give us a different constant, and it will be a constant that cannot be combined with the first one. So we will need to distinguish between the two constants. You'll see in a second here. But let's go ahead and clean this up. So this reduces to 5t, oops, still to the 4th, minus that 18t to the 8th plus 6t squared plus our c1. Okay, so then, like I said, we're going to do this again. Just take the antiderivative of both sides. So then we will just get y on the left, and we have to do our antiderivative again here. So this is going to come out to 5t to the 5th all over 10 minus 18t to the 9th over 9 plus 6t cubed over 3 plus c1 times t. That's a constant. When you take the antiderivative, it'll be c1 times t, and then we get our new constant. And here's where you can see why we have to distinguish between the two. There are two different ones, and they're not like terms. They can't be combined. So if we reduce, we get t to the 5th over 2 minus 2t to the 9th plus 2t cubed plus c1t plus c2. And that represents our general solution for that differential equation. Okay, let's try another initial value problem. So we've got a differential equation and we have an initial condition. So just as the previous one, we're going to take an antiderivative. And all of our integration rules still work here. So for this particular example, you might want to do a substitution. You don't have to, but let's just do a substitution. We're going to let u equal negative t over 2, so that du will be negative 1/2 dt. Now, I don't have a negative 1/2 in this integrand, so I'm going to put one in, but that means I have to cancel it at the same time. So if I'm going to put a negative 1/2 back here, then I have to put a negative 2 in the front to cancel it. Okay, so it's still all multiplication there, but this negative 2 will cancel that negative 1/2, taking us back to the original. So now we can do our substitution. So this is really negative 2 times the antiderivative of 10 e to the u du, replacing that with du, replacing the exponent with just u. And antiderivative of e to the u is itself. So this is just negative 20, multiplying those constants together, e to the u plus c, and then we can put the u back in there. So negative 20 e to the negative t over 2 plus our constant. So what we have here is the general solution. So we want to get the particular solution, which is where the initial value comes in. So let's plug that in. We need to do y of 0. If we plug 0 into this, we have negative 20 e to the 0 plus c. Well, that's going to just give us a 1 there, so negative 20 plus c. And we know y of 0 is 4. Right? We're given y of 0 is 4. Add the 20 over, you get 24 is your constant c. So then we can write out the particular solution for the initial value problem, which would be negative 20 e to the negative t over 2 plus 24. So that is our particular solution, and it's graphed over here. You can see that the initial value, if you plug 0 into this, it starts at 4 and then goes on from there. Okay, let's look at an application problem. Okay, so it says a stone is launched vertically upward with a velocity of v0 from a point s0 meters above the ground, where the initial velocity, v0's initial velocity, is positive and the initial position is greater than or equal to 0. It says assume that the stone is launched at time t equals 0 and that s of t, the position of the stone, is the position of the stone for t greater than or equal to 0. We're going to assume that the positive s-axis points in the upward direction, so positive motion is going up. By Newton's second law of motion, assuming that there is no air resistance, the position of the stone is governed by the differential equation s double prime of t equals negative g, where g is the gravitational acceleration constant. So that is a differential equation, because you have an equation involving one or more of the derivatives of a function. We're going to start by finding the position function for the stone at all times t when it's above the ground. So to do that, we're going to do antiderivative, obviously. So to get s prime, which, let's make that a little cleaner. To get s prime, which is the same as the velocity function, then we will take the antiderivative of s double prime of t, which would be the antiderivative of just negative g dt. This is not a variable here. This is just a constant. So that's really the antiderivative of the integral from the integral of negative 9.8 dt, which would be negative 9.8 plus some constant. Oops, sorry, 9.8t. Right, antiderivative of the constant would be 9.8t. Okay, but we know that the initial velocity, by definition, is v evaluated at 0. So if we plug that into this, negative 9.8 times 0 plus c, this is going to get wiped out, and you get v0 is actually the c. So this really could be written as negative 9.8t plus v0. So the velocity curve, the velocity at time t is just given by that. Okay, so let's get rid of this. And now we want to find position. So we know that position should be the antiderivative of s prime. But s prime is also v, so this is really the antiderivative of v of t dt. And we just found that over here. So antiderivative of negative 9.8t plus v naught with respect to t. So that's going to give us negative 9.8 over 2 times t squared plus v naught t plus, again, another constant. But again, just like the previous one, we know that s of 0, by definition, s naught I should say, is s evaluated at 0. If we plug 0 into this, we get negative 9.8 over 2 times 0 squared plus v naught times 0 plus c. And as before, those get wiped out, which means s naught is really c, or yes, is c. So let's put that in. So negative 9.8 over 2 t squared plus v naught t plus s naught. And that gives us our position function at any time t. And this should correspond to the same function that you use in your physics class as well. All right, so let's go to part B. Part B says, at what time does the stone reach its highest point, and what is the height at that time? So there's a couple ways you could think about this. You could just look at the position function and say, hey, that's a parabola. And I know that it will reach its highest point at its vertex, and the vertex of a parabola would be when t is equal to negative b over 2a, meaning when it's equal to negative v naught over 2 times this, which would end up just being negative 9.8 on the bottom. So you could do it quickly like that, but let's take more of a calculus approach. So the calculus approach would be that when the object is going up, it hits its highest point and it briefly stops and then comes back down. When it stopped, that is when the velocity was equal to 0. So the highest point will be found when we just solve the equation 0 equals v of t. In other words, 0 equals 9.8 t plus v naught. So we solve this, divide over, t will be equal to v naught over 9.8. So anytime, this is true as long as there's no wind resistance, if you shoot an object straight up, the amount of time until it hits its highest point will be the initial velocity divided by 9.8. Okay, so that answers the first part, right? That would be the number of seconds that it would take to hit the highest point. But then it says, what is the highest point? So the highest point comes from us plugging into the position function, which I should have had written out here. So we need to take this expression and plug it into this function. So s of v naught over 9.8 plugged into all that. Okay, so then we try to clean this up. So notice this square needs to be applied to both of these, but when it's applied to the bottom here, one of those is going to cancel. So this could be written as v naught squared over negative, I guess. We still have a negative. And then the bottom would be 19.6, because we do get to multiply that once. And then this is plus v naught squared over 9.8 plus s naught. If you get a common denominator and add these, you are just going to get a positive v naught squared over 9.8 plus s naught. So this expression represents the actual maximum height that the object will reach. And again, this is going to be true in general, provided you're on Earth and provided there is no air resistance. Take the initial velocity, square it, divide it by 9.8, and add the initial height, and you know how high the object traveled. Okay, so then for part C, it just says, okay, well, find out which one will go higher. If you have an initial velocity of 39.2 meters per second, but you shoot it off at ground level, compared to a slower initial velocity, 19.6 meters per second, and a initial height of 50 meters, which one actually goes higher? So let's label these as case I. Okay, this was the expression from our previous step that represents the maximum height that the object travels, so we just need to plug everything into this. So plug in for the first case, we've got 39 39.2 squared over 19.6 plus 0 in this case. The initial height from this first case was 0. That comes out approximately to 78.4 meters. And then for the second case, this one has an initial height of only 19.6 meters per second. Got to square that over again 19.6 plus 50. This one you can actually do fairly easily without any extra computation. One of those 19.6s is going to cancel, so you end up with 69.6 meters. So we can see that this was going to go higher. You can have an initial height of 0, but with the initial velocity being twice as much as this, it will still go higher. Okay, one last example. So the problem says, imagine a large cylindrical tank with a cross-sectional area of capital A. The bottom of the tank has a circular drain with cross-sectional area lowercase a. Assume the tank is initially filled with a height with water to a height of capital H, and then according to Torricelli's law, pretty sure that's how you pronounce that, the height of the water is as it flows out of the tank is described by the differential equation that's given here. So the derivative of the rate of change in the height is equal to some constant multiplied by the square root of the height. The way this would typically be written out in a physics textbook is you would say that the rate of change in the height is directly proportional, because we're multiplying it by a constant, directly proportional to the square root of the height. So we saw those kind of variation type statements back in college algebra. I think we did a little bit of it in pre-calc as well, and those show up a lot in differential equations. Okay, the constant that you get here in front, he already has solved for that. It is the cross-sectional area of the drain divided by the cross-sectional area of the tank itself, multiplied by the square root of 2 times the gravitational constant. It's the same constant that we used in the previous example. Okay, so the first part says, according to this differential equation, is h an increasing or decreasing function of t? Well, we studied increasing and decreasing functions way back, probably chapter 3 or chapter 4, and we said that for a function to be increasing, the derivative of that function had to be positive, and for it to be decreasing, the derivative had to be negative. So if we look back here, we've got the derivative, and we know the derivative is equal to this expression. Square root for us is always going to be a positive value, so we don't have to worry about that. And if you look at k, well, k is the ratio of 2 cross-sectional areas multiplied by another positive number. These are positive, this is positive, so k is greater than 0. Should say greater than or equal to. I guess it could, the hole could get plugged, but we got this negative out in front of it. So that shows us that h prime of t is less than 0 for any t greater than or equal to 0. So that implies that h is decreasing. That should be pretty obvious. I mean, we've got a hole here, the water is draining out, so the height should be going down. So h should be a decreasing function. Okay, step B says to verify that this equation this function is actually a solution to that differential equation. So this is just like what we did at the beginning. We need to take a derivative. So little h prime, we have to use chain rule here, so bring the power down, leave the inside alone, decrease the power by 1. But then I have to multiply by the derivative of the inside. Right, this is just the inside of that. Oh, I lost a minus sign there. Oh, better make that smaller. Okay, so now when we differentiate this, let's rewrite this, leave it how it was. And we don't really need the 1 up there. So when we differentiate this piece here, remember that capital H is a constant. This was just the initial height, so that's just a number there. So that's going to get wiped out when we differentiate. And then when we differentiate this piece, k over 2 is another constant. Really, it's negative k over 2. So we're really taking the derivative of a linear function. So the t is just going to go away. We're just going to get negative k over 2. This could be brought to the front, and you can see these cancel. And so what we end up with is negative k times the square root of h plus kt over 2. Now notice, if you look at this carefully, actually we'll just write it out. So this right here is h prime. And what we have to verify is that h prime is equal to this expression here. So let's do that. Negative k square root of h. So this is supposed to be h. I just need to put it inside there. So negative k times the square root of h plus kt over 2 all squared. So notice, obviously, the square and the square root cancel each other out. So this just leaves negative k times the square root of h plus kt over 2. Right? That square and the square root canceled, and you can see these are exactly the same. So that means that h prime is equal to this. So we verified that this satisfies both sides of that equation. So therefore, h equal square root of the initial height minus the constant times the variable over 2 squared is a solution. Right? It is a solution to that differential equation. Okay, part C says take that solution, the one that we just verified was a solution, and graph it for an initial height of 1.44 meters, a cross-sectional area for the tank of 1 square meter, and a hole of cross-sectional area 0.05 square meters. So to graph it, we just use the calculator. So to keep it accurate, I stored the h as capital H. Then I plugged everything into this. Put the 0.05 in for little a, divided by 1 for the capital A, and then 2 times the g, stored that as k. And then I just put the whole function, all of h, into y1. I don't think this is something that I've shown much for your calculator. If you want to manually put something into y1 without going to the y equals screen, you have to put the function in quotes, and then you can store it as y1. This is a convenient way to enter really messy functions. I wouldn't consider this one messy, but it is a handy trick. It also is useful if you're going to write your own programs. Okay, so we got it in y1, we graph it, and we're supposed to find, maybe that's what part D was. Hold on one second. Okay, I forgot to copy over part D. Part D said, find how long it takes until the tank is empty. Well, the tank being empty means h should be 0, right? The function itself should be 0. So over here, that's what I did, is I found, it looks like I did the minimum, but I should have just done when it's 0. So you could do either one, find the 0 or find the minimum. And we can see that occurred at this x value. And remember, for this, x is t. So that means the tank will be empty after approximately 10.842 seconds. Okay, and I believe that's the final part for this, so hopefully these notes made sense to you. Email me if you're having trouble, and we'll see you on the next video.